This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Cool.
Ready?
Yeah, ready to go.
So, welcome back to this second session of the first day. And it is a great pleasure to have here Nathan Wiebe, who is from the Center for Quantum Computation and Quantum Control at the Department of Computer Science of the University of Toronto.
Great.
And we are very happy and pleased to have you here, because you will tell us.
Wait till I'm finished talking. Maybe you won't be as pleased.
But we are very, looking forward to your talk, because you will tell us all about quantum neural network and whether they really are the classical, correct classical counterpart. So, Nathan.
Great, wonderful. Thanks a lot, everybody, for coming. It's something that's actually kind of surprising. If you take a look at the way the field has grown, this size of a crowd is kind of what I remembered QIP 2010 being. And now we've got a specialized conference on just quantum machine learning that's capable of really having a packed room. And so this is really kind of, I think, cool and something that's kind of amazing. And this talk, I hope, is going to be a continuation in theme to sort of what Marco is taking a look at. And I wanted to begin by just first, of course, issuing this trigger warning down at the bottom. There will be memes in this talk. If you don't like that, please leave. But for those of you who are meme comfortable, then I swear that at least some of them will be good. So one of the things I wanted to kind of begin with is, I hate to do this. This is something I tend not to really do too much, but I'm sorry. The reason why is I might have talked a little bit of trash, especially when some beer's on the table, about variational quantum algorithms and QML, specifically variational approaches to QML specifically. And so this is basically me in a nutshell. I will often end up getting really excited students coming up to me saying, I really want to work in variational quantum algorithms, and that's exactly what I do. I basically end up saying, nuh-uh, I want nothing to do with that. The reason why is manyfold. The justifications that I would historically give for this is that at a high level, we have absolutely no reason to suspect that existing variational approaches that have been proposed are scalable. I mean, if you take a look at this text block, just doing a back-of-the-envelope calculation, and this is specific for variational quantum eigensolvers rather than QML. I didn't do an analogous QML calculation, but just to estimate the energy for a challenge problem for a chemistry application, which looks similar but with higher precision requirements typically than what QML has, we need about 10 to the 20 gate evaluations just to evaluate the objective function for this using existing approaches. And I want to emphasize this. This is just to evaluate the objective function using the best methods that I have at my disposal for compiling this down to individual gates. That is not the bottleneck for this algorithm. The bottleneck is a gradient evaluation and the number of times that you need to repeat that in order to train the model. Typically, people will say, oh, well, we have no idea how many steps we're going to need for our gradient descent algorithm for it to end up converging, so we won't talk about that. And so, rather than us treating this issue like Bruno, yes, I did see that movie, that we need to actually kind of ask, well, all right, how excited should we actually be about this? And furthermore, given the fact that if we want to take a look at an LLM style problem in machine learning that we'd like to be able to tie, there's roughly speaking about 1 trillion free parameters that we end up having inside these models. And the cost, unfortunately, ends up scaling quite poorly with the number of parameters in this. And it's really doubtful that we'll be able to have a comparable depth to the number of, to the size that we end up getting on quantum computers of an LLM. And on top of that, the advantages in terms of sample complexity as well as computational complexity for most applications of QML are really unclear, at least for conventional tasks that we'd want to do in that. So with all of that, this is what I would do to tell people that they should really do something else with their lives. Okay? But one of the things that, and yes, this is essentially what I would be saying afterwards, is that there is basically, from my perspective, no hope for near-term quantum machine learning advantages. And if any of you disagree with me, I'm happy to have a discussion about that over beers later. But the thing is that, as I said, this is my apology for this. Because I did this for years, and I've annoyed a ton of my friends about this, and unfortunately, the point of this talk is that I think I might have been wrong. That the problem, at the end of the day, isn't actually with the overall strategy, the approach of training a set of parameters for it. The problem actually was with the gradient approach to doing this. So the whole story of this talk is to say that, kind of like what Marco was getting at during his talk, is that potentially we need to think more out of the box when it comes to quantum machine learning. And rather than following the exact same approach that we would normally do and consider hybrid algorithms, where we have a quantum computer as an accelerator model for a classical computer that's being used to evaluate some complicated gradients, maybe actually we should not evaluate gradients whatsoever. Maybe what we should do is do the entirety of the quantum computation inside the quantum computer, with no gradient updates being done whatsoever. And the TLDR that we end up getting when we consider all of this, under admittedly some very strong assumptions that we end up putting into this, we end up actually getting costs that end up scaling actually kind of more like the cost of doing a single gradient evaluation for the cost of the entire optimization process. That is why I apologize to all of you, is that conceivably by thinking outside of the box for some of these problems, we can actually end up getting numbers that suggest scalability might be possible for variational quantum algorithms. Now I want to set everybody's assumptions going into this. What I'm not trying to do is I'm not trying to say that these ideas are going to end up leading to something that we could run on existing IBM hardware. Because what happens with this, in order to keep it all in the quantum computer, we need to actually encode bit strings that correspond to each of our variational parameters. And we need to actually simulate dynamics for each of those variational parameters, it turns out. And that would require, using my approach that I will be presenting here, likely tens of thousands of qubits. But you know what a computer scientist calls 10,000 qubits? They call it order 1 qubits. That gets more laughs in my department. But in any case, what I'm interested in here is the question about scalability. Is this approach just screwed from the get-go? And I don't think it is anymore. So let's dive into some more details about this. So as I said before, the big problem here is, as I said, with gradient calculation. This is an example of a cat that I like to call Sisyphus. This is an example where, the gradients might look okay, but we need sometimes a large number of gradient steps in order to be able to get to our objective. And so the basic question is, as I said before, what we'll do in this is we'll give an approach that reduces the problem of QML, essentially variational optimization, to a Hamiltonian simulation problem. We'll run the Hamiltonian simulation problem for it, and there'll be no gradients whatsoever, and the number of steps that we end up needing for the entire process is boundable. So, okay. What's so bad about gradient descent calculation? The problem is that gradient descent calculation is an algorithm that we can actually prove query lower bounds on. And the query lower bound that you end up getting ends up scaling like square root d over epsilon in a limit of small epsilon, where d is the number of variational parameters that we'd like to take the gradient with respect to. So this is the best that a quantum computer can conceivably end up doing for this. And actually, up to logarithmic factors, there exist algorithms that saturate this. So essentially, we found the best algorithms that are possible in general for computing gradients on quantum computers, and the problem is that they suck. The reason why they end up sucking is because of the fact that the error epsilon scaling that we end up getting on the other side is inverse. So, and we can't do better than that. By the way, the scaling with the number of parameters d can be improved by using randomized approaches, but at the price of having order 1 over epsilon squared scaling. So there's a particular asymptotic regime that this is subtly taking. But in any case, the problem is like, let's imagine that we want to take a look at a problem for QML. And the standard gradient calculation problem, the minimum problem that you could take a look at, is I want to find a gradient, and I don't care about the value. I just want to get the sign right. So then, in that case, how large should your epsilon be? Well, your epsilon should be then on the order of the gradient that you're trying to estimate. Okay? Now, the problem is, how do those guys end up scaling? Well, as mentioned repeatedly in a whole bunch of talks, and I was able to delete all these slides, so thank you everybody for saving me time, is that in general, if we end up assuming that we have a sufficiently complicated ansatz, something that ends up looking like a random circuit coming in, then effectively our states end up scrambling over a very high dimensional Hilbert space, and the values of the gradients that we typically end up expecting for this will be exponentially small. Meaning, when we end up plugging this into the epsilon scaling that we end up getting from our optimal algorithm, we end up getting costs just for a single gradient evaluation that are exponentially large. And again, this is optimal. If we end up kind of pushing this in, the total number of steps, the total number of operations that we would end up needing would be linear in a number of steps. And if we end up considering this to be some, L being some like physical distance between the two, the number of steps that we would end up needing would be like, proportional to the typical size of the gradient divided by some learning rate lambda. And basically, this ends up suggesting that we will need a ton of steps for this under the assumption that we end up having one of these barren plateau type settings coming in. And the question is, what is the thing that made this so awful? Well, the real bottleneck for all of these algorithms is actually this process. It's the part that all of you love, right? It's the fact that that variational algorithms effectively are hybrid algorithms. There's something where you could get your data from the IBM quantum computer. We can learn it through sampling or through amplitude estimation. I was kind. I assumed that we're doing it with amplitude estimation, not sampling. But regardless, we have poly 1 over epsilon cost at getting values from that. Then, once we've got those, awesome. We can throw those into a Python and set that into any of your SciPy optimizers or anything you feel like in order to be able to find the best parameters. So this is what everybody loves, and this is what minimizes the barrier to entry in order to be able to get into this. The problem is that effectively, we have to spend these 1 over epsilon costs just to interface back and forth between the two of them. So think about this kind of like serialization. What you're doing here is we're spending a ton of resources in order to be able to learn these values so we can communicate it with the classical world. So the classical computer can make an update, and we'll have to repeat this process over and over and over again. Okay? And the key thing is that if we do all of this inside the quantum computer, then we don't need to spend these order 1 over epsilon costs to bring it back and forth. Now, this doesn't totally ameliorate the problem, obviously, because what this ends up meaning here is that the order 1 over epsilon cost for the gradients is something that we expect is kind of fundamental. If we do this all on a quantum computer, though, we don't necessarily need to learn the gradient via phase estimation. So 1 over epsilon cost doesn't actually need to end up coming in, because we don't explicitly need the gradient to be passed back and forth if we're not doing this in a hybrid way. So that is the basic advantage to it, but it does partially, but not totally, ameliorate the issue of barren plateaus. The reason why, as I said before, is that the barren plateaus kill us because of our accuracy requirements. Because we need to be able to use a number of resources to communicate back and forth at scales like 1 over epsilon, the cost is going to be exponential just as a single update. But if this cost can end up scaling like log 1 over epsilon, and we do it all in the quantum world, well, that barren plateau isn't actually necessarily so bad directly. Now, it may require a very large number of gradient steps to be able to do this, which is why it's not a total savior, but it definitely does remove the problems of having a single point or an isolated number of points with incredibly small gradients. All right, so that's the basic idea. And this is exactly, by the way, this isn't a totally new idea. This is the same idea that led to the optimization of linear systems algorithms through linear combination of unitaries methods that was used to make HHL have much better scaling with epsilon. Effectively, the reason why HHL had lousy scaling with epsilon is because you needed phase estimation with the OG version of it in order to be able to compute the eigenvalues and pass them back and forth. By figuring out ways of avoiding the explicit eigenvalue calculation, they exponentially sped it up. We're doing the same thing here. Okay, so let's take a look at the approach. The approach at a high level here is what we'd like to do is we'd like to be able to rethink how we're approaching variational algorithms. And the way that we're doing this is, let's imagine now that we change our problem around. Instead of our variational parameters being classical objects that are sitting on your laptop, now we've brought them into the quantum world. Now, if they're in the quantum world, we can actually think about them as dynamical objects. So the way we approach this is we say, okay, let's think about all of our parameters now as being particles at particular positions. And our objective function now is going to be some kinetic term that we end up creating for our particles, i.e. our fake parameters over here, and a potential, which is our objective function, effectively. And then what we'd like to be able to do is we'd like to be able to set up some system where the natural quantum dynamics of this will end up leading us into a configuration where we can minimize the potential energy for it. And that's effectively how we're trying to approach this. Now, I found out, actually, this always sucks, and this is why I recommend none of you should read papers. I found out some other people had similar ideas. They call it like Hamiltonian gradient descent or something like this. Never read papers, it's the worst. So, except mine. Right? I should mention that one thing that's kind of interesting about this is that the way that we set this up is that, interestingly, if we end up translating this over, we have a number of different choices that we could end up making for these particles. And we consider both of them in the subsequent slides. We'll consider the particles to either actually be quantum or classical. It doesn't really matter which. There's one thing, though, if you pick them to be classical, this will cause you a heck of a lot of nightmares. So, one of the things, I don't know about you, but I had overzealous physics professors who would always say that the weird thing about quantum mechanics is that position and momentum don't commute. But when you spend your entire career doing quantum mechanics, it is so weird to go back to classical and having position and momentum commuting. That taking these particles to have a momentum that commutes with their position caused us no end of pain over here because we kept on assuming that the wrong commutation relation. So just bear in mind if you do that, but at the end of the day, both of these approaches can be used, and at some level, you're kind of just building a larger auxiliary system, and you just want to be able to build a system in an appropriate way that'll solve the optimization problem as quickly as possible. Now, I wanted to just put this in a little bit of context. Unfortunately, I don't have time to go into detail about the host of Hamiltonian simulation techniques that are needed here. But at the end of the day, we primarily are going to be using the technique on the right here and the center one, which are post-Trotter-based quantum simulation methods. The one in the middle, a linear combination of unitary simulation schemes, is pretty much like the most flexible set of simulation methods that we have at the moment. And they have a really amazing feature that's not upheld by qubitization on that side. And that feature is that it actually allows us to simulate time-dependent Hamiltonians easily on it. And this is relevant, and this will be hugely relevant here because of the fact that what we'll want to do is, in some cases, we'll want to do a transformation to a rotating frame in this, and specifically the rotating frame of our objective function. And the reason why is that it turns out we'll end up getting much better scaling with our condition number than actually was commonly believed to be possible using existing methods by taking advantage of this. And the reason why this is such an important thing is the linear combination of unitary simulation scheme. Its complexity doesn't actually depend on the maximum value of the derivative. Its complexity scales at most logarithmically with the maximum value of the derivative of the time-dependent Hamiltonian. So if you got a big-ass mofo term in your Hamiltonian, which I think is the technical term, that term, if we go into the interaction frame of that, because we only pay a cost that's logarithmic in that big piece you're going into the rotating frame of, we can actually simulate those big guys in log time, which is amazing. So by picking a good frame for this, which necessitates a time-dependent Hamiltonian, this middle approach actually can really save us a lot. However, I should mention that qubitization is one that frequently ends up getting used, and also in this work, because of the fact that it formally leads to optimal Hamiltonian simulation methods, meaning that there are some problems where qubitization saturates proven query lower bounds for performing the simulation. So in general, if you're simulating Hamiltonian or you don't know anything about the structure, qubitization is your game because of the fact that it is provably the best that you could possibly ever hope for at least some Hamiltonians. But unfortunately, it doesn't work so well with time dependence. So we'll, in some of the slides, I'll be hybridizing these two approaches. Oh yeah, by the way, these are totally unbiased reference papers that you can look at in all of these techniques. All right, so what we want to do first is, in order to reduce the problem of optimization of our QML problem into a Hamiltonian simulation problem, we're going to begin by using this approach known as a Koopman-von Neumann formalism. And the basic idea behind the Koopman-von Neumann formalism is that it takes advantage of the fact that if we take a look at phase space mechanics actually follow unitary evolution as well. And that by doing a simple transformation where we end up saying, okay, well, let's let the phase space density rho be represented by a wave function such that the wave function squared is equal to the phase space density, then actually the time evolution that we end up seeing for this phase space density ends up following that exact form in the middle, but acting on the Koopman-von Neumann wave function, which is the square root of the probability density. Meaning that inside this formalism, what you can do is you can end up translating the phase space evolution to a Schrodinger equation. So the idea then is if we can end up finding a Liouvillean that ends up leading to the correct dynamics that'll cause us to focus, at least in some reduced subspace of the overall dynamics, on like a low energy sector, then life is good. And the question is, well, you know, have such Liouvilleans been studied? And this actually is such a Liouvillean. This is known as the Nose-Hamiltonian. It was discovered ages ago by folks in the molecular dynamics community. And basically the idea here is that what we do is we introduce a bath to it, as you always do when you're trying to simulate something that's dissipative. We build an auxiliary system, and this auxiliary system has a variable s associated with its position and a momentum p sub s conjugate to it. You can end up showing, actually, that the microcanonical distribution that you end up getting of this system ends up actually corresponding to the canonical distribution that we would end up getting for the reduced system of x and p. And so the basic strategy behind this is that, okay, cool, if we want to be able to find the global minimum, and I emphasize global minimum here, of our function, because we're not using gradients here. So why bother, you know, just why not shoot for the stars? Let's go for global optimal, right? Then in that case, we would just set t equals 0. And that will end up corresponding, once we reach equilibrium, if we can prepare a microcanonical state for this, to the minimum of our QML objective function. Okay? And in particular, the potential that we would look at here is for our quantum state, psi of x, we would just take a look at the expectation value of f. I'll talk a little bit about how we could actually do this. So visually speaking, using my totally unfinger-painted art here, what we want to do is we really want to be able to set our t inside this Liouvillean to be sufficiently low, so that way we can prepare a thermal distribution over the low energy sector of this, and eventually cool it into a minimum energy configuration here. So the way that we end up doing this is because of the fact that the Koopman-von Neumann formalism gives us a way of translating our dynamics into a quantum setting. Well, guess what? We can use quantum thermodynamics or the quantum thermalization literature for this. So in particular, we'd like to be able to figure out really what the distance is between the infinite time average, which is what I've got at the bottom, and the microcanonical distribution. And so the way that we go about this is we say, okay, well, actually, we only care about achieving the microcanonical distribution over position. Because position is the only meaningful thing, right? As I said before, the momentum for all of these fictitious parameters that we put into our system, corresponding to the variational onslaughts, has no physical meaning at all. So we only care about getting the right distribution over position. So we are now going to treat the momentum as a Bath variable that we're tracing over. Once we consider that, we can end up using this beautiful result by Short, Linden, Popescu, and Winter. That ends up showing the following relationship between the infinite time average that we end up getting for these systems under the assumption that the state is effectively Haar random inside this energy window, delta, that we're taking a look at. And then we end up getting that the trace distance ends up scaling as follows, where these are the dimensions of the individual registers that we end up having. So if we end up having that the dimension of position and dimension of momentum are the same, that cancels. And by increasing the dimension of S, i.e. the number of bits of precision even, that we're using in order to be able to specify the Bath variable S, this actually will end up shrinking. And so then we can provably end up getting, under the assumption of Haar randomness for these vectors, arbitrarily close distributions in the infinite time average to this state. Problem is that in reality, we don't actually get the ability with a finite amount of resources, despite my best efforts, to simulate infinite time dynamics. So we have to figure out how much time is needed, and this ends up depending on the spectral gap that we end up seeing for the overall Liouvillean. So when we consider the error that we want, if delta is our error, then the total amount of time that we end up needing in order to be able to equilibrate under all of these assumptions ends up scaling like that. Gamma here is the gap of the Liouvillean here, and delta is the error that we're willing to tolerate in this. Okay? So that is basically how that goes. Now, the question is, all right, well, how do we go and convert how do we convert these, the value of our objective function to something we can compute? Easiest way to do this is to use the Hadamard test circuit. Hadamard test circuit has the property that the expectation value is given by the probability at the top. So now you're thinking, hey, whoa, bro. What are you doing here? This is just some variational stuff, isn't it? Hold on. Then what I do is I use amplitude amplification. Why do I use amplitude amplification? I am not using it in order to get an outcome of 0. I don't care about the outcome, actually, whether it's 0 or 1. What I care about is the fact that amplitude amplification can be viewed as a method of transducing a probability into an eigenphase. Once it's converted into an eigenphase, then we can use it actually to kick back the value of the objective function inside a unitary that we can then manipulate. So in particular, what we do is we first convert it like this. Then we use quantum signal processing, which at a logarithmic overhead, we can use to undo the arc sine in the square root. Basically, we do a sine squared transformation in the exponent. There's actually even closed forms that you can do, which are analogous to the Jacobi-Unger expansion, that allow you to do this. So now we can turn this into an exponential of the probability that we wanted, plus the offset. The offset is actually quite important, but let's ignore that. Then what we can do is if we want to block encode the gradients here, not compute them, block encode them, so build them inside a larger unitary so I can feed them into the quantum simulation algorithms, which need this for the Liouvillean equation of motion. Then what I can do is I can use a finite difference approximation to the derivative. Like this would be the simplest centered difference one, but I can make them bigger and bigger and bigger at logarithmic cost in order to make it so I don't have to have a tiny value of delta over here to be able to compute that. So that is basically the idea. And then once we've done that, we go to Appendix B of Andras Gillian's paper on not linear programs, some STPs. And then that will tell you how to do a logarithmic block encoding to be able to undo this gradient and convert it back into a gradient in general, inside a matrix. All of these overheads are polylogarithmic. So what this ends up meaning is this gives you a way of building a unitary that contains all of this gradient information without actually needing to estimate it. Cool. So when we put this all together, this is the overall complexity that we end up getting for it. And you'll notice that here, this delta is the only kind of thing that looks like an error that ends up coming in here is actually the error that we end up getting from the infinite time average. That's the dominant bit. The actual simulation error is trivial. And further, we don't care about how many time steps or gradients that we end up needing. Everything, if we use cubitization, is just linear in this. However, the efficiency of this is really dependent upon the assumption that the variance that we're looking at here, this V of delta, is small and the Liouvillean is gapped, which in the continuum we don't generically expect. But at the very least, what we can do is we can, with these methods, show that if those hypotheses are met, that actually this algorithm it's going to run in a reasonable amount of time. And it isn't just a gradient calculation. I want to emphasize that this is the overall algorithm in its entirety. So that's the first approach. Let me show you another approach that we consider. This approach, the previous approach, is a shoot for the moon approach. We try to find the global optimum with that. But in QML and in general, we usually give up on this hope of finding a global optimum. After all, if we could find a global optima, then there's many problems in NP that we'd be able to solve either on a quantum computer or on a classical computer, both of which we don't believe is generically possible, at least for the NP hard problems. So the idea is, if instead we want to do this, let's take a look at a local optimizer. How could we build quantum dynamics that would actually give us a local optimizer rather than a global optimizer? Rather than thermalization, which is more analogous to a quantum walk, what we do here is we say, okay, well, what if we took a look at dissipation? So this is the standard problem. You know, we consider putting a mass in some viscous fluid over here, displace it, and then this will continue until it eventually reaches its equilibrium configuration. Problem is, it's a dissipative process, and quantum dynamics and Hamiltonians don't actually work so well in that setting. However, it turns out there's a hack. The smart people have figured out that actually there's a time-dependent Hamiltonian that effectively can be used in order to be able to simulate dissipation. So what we do is we just use that dissipative Hamiltonian. And we run that, and we would like to be able to show that if we start the oscillator off sufficiently close to a local optima, then actually we'll get fast convergence with this method. So that's what we're going to be showing, is that effectively if we have a strongly convex optimization problem, which means one that kind of locally ends up looking like it's quadratic around a local optima that you're looking at, then we can actually end up showing bounds on the number of the resources that we need in order to be able to simulate this Hamiltonian using the framework that we discussed in order to find the optimum parameters for our QML problem. So basically, that's exactly what we do with this time-dependent Hamiltonian, and then we end up finding this scaling coming out the other side. HF over here is the norm of the Hamiltonian that ends up corresponding to our function that we want to compute. D is the number of variational parameters that we're looking at, and epsilon is the error that we're willing to tolerate in our answer that we hit the end. And I should mention, the variational parameters here, one of the reasons why we don't need to sample for this is because of the fact that all the variational parameters are encoded in bit strings at the end. So if we just do a single run, and this thing actually is minimizing into the bottom, we can just read out literally all of our variational parameters in a single go. So that's why this doesn't need to be repeated more than once. And the other thing that's fascinating about this is that actually the cost of the overall simulation here is actually pretty much identical to the cost of a single gradient evaluation using the lower bound that I showed you earlier. So this ends up suggesting actually that in principle, at least if you're lucky enough with this approach, and you can find an initial configuration that's close to a local optimum, then the entire optimization procedure can be done on a quantum computer for roughly the same price that you would do a single gradient call, which is pretty awesome. Also, I should mention that this is done using the Liouvillean corresponding to this. If we take a look at another approach, if we end up assuming that our objective function is given by a bit oracle rather than the probability calculation that I showed you how to do using that like 5-step process involving amplitude amplification and the Hadamard test, if we just have some function that ends up kicking that out, then actually we can do something one step better. As I said before, we can go into an interaction frame of our potential. And then, once we end up going into that interaction frame, we can end up actually getting scaling that ends up looking like this. Now, it's interesting because ordinarily for these problems of gradient descent, we end up getting complexity that ends up scaling like the condition number. It scales polynomially with the maximum eigenvalue divided by the minimum eigenvalue. This ain't like that. Notice the maximum eigenvalues inside the logarithm. And this is a benefit that we end up getting from using these quantum mechanical effects to go into a rotating frame. We'd be unable to take advantage of this optimization in a hybrid-based approach. But here, by doing everything inside and by translating the problem to a dynamical simulation problem, we can take advantage of these optimizations and totally blow the complexity that you would end up expecting for this out of the water, at least in cases where lambda max is large. So one of the things that I should mention, then this is a key thing that is a caveat both behind this scaling and the previous one, is that it's very difficult to be able to prove discretization errors that we end up getting in the continuum, in part because of the fact that the continuum Hamiltonians are formally unbounded. So there's going to be some input states that you could end up getting in that'll have really bad continuity to them, for which actually pretty much any bound that you can write down will be violated. So it takes a lot of work to be able to do this, and so we assumed at the moment here with this scaling that discretization error is negligible, and this is relevant because of the fact that we're putting actually more and more pressure on the discretization error by going into the rotating frame. So I did want to mention that there's caveats here, and this may not actually necessarily hold up for all problems, but for problems for which the discretization error is negligible, actually we can get better scaling than what you would expect would be the best possible scaling that we could get otherwise. All right, so to conclude, for a long time, honestly, I was terrified about the complexity of variational algorithms. I really felt that the cost of doing all the gradient updates that we need meant that fundamentally these were unscalable algorithms. And so the important thing about this was that, oh gosh, my memes were in the wrong order, is that as I suspected, I was right all along. That this is a problem. But importantly, as this a meme that was totally not generated by me a few minutes ago, points out, actually we may not need to compute gradients in order to learn. This is an important thing for us to approach the problem classically. But quantum mechanically, this may not actually be the right way of us approaching it, because after all, we don't care about the gradients. It's not usually teaching us anything. And because the cost of learning things in quantum computing is so high, if we can avoid learning something, we should. And so for that reason, actually, I'm of the opinion that many of these scalability issues that I've worried about in the past disappear when we're taking a look at these new forms of entirely quantum optimization that are going into it. So to that end, well, of course, I was right all along. There was a way I could have been righter. And, I'm humble enough in order to admit this to you all. But going back to kind of what Marco ended up saying is that I really do feel that we need to think out of the box when we're coming to this. This suggests that the gradient problems that we were taking a look at likely have, at least in asymptopia, some solutions. But this doesn't actually address all of the problems that we're taking a look at. This doesn't address the question of why should we be using these models, and whether or not there's actually some killer application for quantum machine learning coming out the other end. And this is something that we as a community need to think about more. And, oh, whoops, I thought there was another meme, but there wasn't. So this is something that I would challenge us all to think about. Just like in this case, my own personal lack of vision didn't lead me to think about these types of approaches for a very long time. I think as a community, we need to take a step back, think more about the basics and ask, how best can we end up using quantum computers in order to solve the tasks that we want to solve with machine learning, rather than merely mimicking the details of a machine learning algorithm? Thank you very much.
Time for questions. A lot of questions.
Hi, thank you very much. This was very good. Sorry for going back to a point that you deliberately skipped over. So, is there a short explanation for how does this relate to this quantum Hamiltonian descent? And to these other papers on like local minimum of quantum systems that have proposed thermal bias optimization.
Yeah.
Thanks.
So, okay, there's an easy answer to how it relates to quantum Hamiltonian descent. It's the same idea. It's just we weren't aware of this going in. At the end of the day, there's actually a couple of things that I think we do a little bit better than many of the other papers. Our use of the interaction picture transformation leads to a little bit better scaling than what these methods could show. And further, I don't believe that these methods ended up actually showing a great way of dealing with the block encoding issues of the objective function. So it's not as obvious how to do this apart from the case of you being given a bit oracle, how you can apply it. And still, even in that case, they failed to get that log factor because of the transformation. But still, nonetheless, I think spiritually, many of those papers kind of had the right idea, but I think that they just stopped at the finish line. Oh, it's fine. You could end it with just great talk.
No, great, okay. I know it anyway, so great talk, wonderful. Along similar lines, you mentioned this comparing idea of like mapping the optimization into a Hamiltonian problem and then use ideas of equilibration and thermalization to get a kind of convergence guarantee. But the time scale results you mentioned, they're like in expectation, meaning you get a guarantee that you are kind of close to the infinite time average for most times, but you wouldn't quite know when this happens. Mm-hmm. Is this a problem for your algorithm? I mean, do you need a guarantee when it happens, or do you just need to sample over different times?
No. This isn't a problem for the algorithm unless you're one of the reviewers.
I'm not.
Okay, then it's not. At the end of the day, what we do is that delta scaling that we end up seeing in the end is all coming from Markov inequality arguments. So what we do is we want to talk about the probability of a large deviation from the expectation. And because of the fact that we're randomly choosing the time in the algorithm, then it's fine.
Yeah. Thank you.
Great talk. In approach 1, you linked the time it takes for your approach to the spectral gap of this Liouvillean. Mm-hmm. What is the spectral gap typically? So you said, in the worst case, it's exponentially small.
Yeah.
What situations do you expect this to only be polynomially small?
Okay, it's an excellent question. So one of the problems that ends up coming in here is that as we end up approaching the continuum limit for the Liouvillean, typically what we're going to have is we expect the eigenvalues to get closer and closer and closer, so that the gap that we're looking at should end up shrinking actually to zero inside that limit. But on the other hand, we expect actually in that limit for all of the for the high eigenvalues or vectors to be kind of comparable in terms of their phase-space distribution. So at least if you were to picture it as a Wigner function going out. And so in general, we don't expect this to be such a horrible problem, but it actually, conceivably is. And also, what we would want to do if we want to be able to get inside this regime where it would end up working well, is we'd want to purposefully not discretize it down to that fine level of granularity. We'd want to be able to keep it so that the gap remains relatively large and cross our fingers and pray that that's going to be enough for our purposes. But again, I should mention, what we're trying here is we're trying something absurd. We're placing bounds on the total amount of resources needed in order to be able to reach the global optima. We do not expect that a quantum algorithm in general can, in polynomial time, find the global optimum. But we just wanted to be able to give results that actually talked about an end-to-end algorithm, theoretically, even if those bounds, in some cases, like actually the typical case, would end up being exponential.
Thank you for the great talk. I'm just curious, you mentioned the hack of simulating a dissipative Hamiltonian. Will there be any benefit to simulating the open system dynamics directly? Is there any advantage?
Yeah, so that's a great question. Whether or not we could get some advantage by directly simulating the open system dynamics. One of the problems is that in general, what we want for this is we want to be able to take a look at a set of, say, jump operators for a Liouvillean, like a quantum Liouvillean specifically, that would end up leading to concentration that we can actually bound and prove something about. We picked these models because of the fact that they're simple enough that we could actually prove something about the resulting state that we end up getting out the other side. Often, if you pick an arbitrary set of jump operators, it's not going to be clear what's happening. So you can totally do it, and it may actually be the right thing to do, but there's a tension about why we were doing this. We wanted to do it for analytic simplicity, which is why we worked with classical rather than quantum Liouvilleans.
Okay, I think we had enough question. Time is
Okay.
is short, so maybe you can ask your questions later, maybe later. So thank you.
Thank you very much. Thank you.